Okay. So particularly I'm interested to see how is my voice. Is it loud and clear? So if you can listen to me. So it's going to be it's going to introduce a little bit of echo, but I think it is okay. Is it loud and clear? Is it loud and clear? Okay. Nope.
Miten muuten Aki asiasta kukkaruukkuun? Mä sain Lutinon kun tämmöisen hupparitilaulinkin, niin mikä koko sulla on? Se Lutinen.
Mä en muista.
Et muista?
Se on kyllä mun tuossa toimistossa.
Joo.
Mä en muista.
No niin.
Joo, se on hieno huppari.
Joo, mä ajattelin, että semmoista nyt tarjotaan, niin täytyy laittaa tilaukseen.
Eikö sulla ole mahdollisuus kokeilla sitä? Oot se mun kokoinen suurin piirtein? Mulla on kyllä aika paljon leveämmät hartiat.
On kyllä V-muotoon
niin se ei ole mahdollisuus kokeilla. Eikö tuolla... Mä en kyllä muista mikä mun koko on. Se on L tai XL. Silloin kun ne tuli meille, niin meillä oli mahdollisuus kokeilla ne koot. Okei, mä käyn hakemaan tein. Mä tuun sitten takas. Aha. So this is not okay. Okay, how is it YouTube? That's perfect. Good. So it's crossing my like this much?
No, you forehead.
That's important because I had a haircut on Saturday. People would not recognize that otherwise. Thanks. In 4 minutes. 4 minutes.
So what's your topic? Did you choose one from the examples that you made it up?
No, like the turbocharging? Yeah, turbocharging.
Turbocharging.
For automobiles.
Jahas, hyvää päivää Joona. Oikein. Etupenkin poikia. Joo, ei siis, jos tuolta tapahtunut joskus ollut tuolla, niin sieltä nää pitäisi vakipiirtää. Sitten täytyy kuitenkin katsoa YouTube, että ei ole mitään järkeä.
I think we should shoot a 5 minutes
Mites onko te valinnut siinä? Mikä se kurssi on se digitaalinen design? Onko te valinnut? Oletteko te niistä valmiista? Oli super spesifiä.
No, he is the bus card he can buy and take from your park. Okay, I'll say.
Vaiheessa se on.
I think we have.
Ai siis teillä oikeesti kuvaa. Joo, se on täällä.
I saw sometime in lecture slides
Ai niin, mikäs
AI and mechanical engineering or something.
Yeah, right.
Missing.
Yeah, it is missing. It's missing. So instead of this artificial intelligence and mechanical engineering, we're going to discuss about something a little different. That's going to be whizzing lecture. I mean, the lecture number 12. That was earlier. You're right. So it was like artificial intelligence and mechanical engineering. But I decided to use a visiting lecture and a summary what we have discussed so far. And then the last lecture will be career counseling plus coffee service. How that sounds? Okay. All right. So, yeah, exactly time to get started. Respect. I haven't really made any of the editing. I made a few editings in the beginning of the period number 1, and then I somehow don't do it anymore. But usually I use this trick, this respect, and to know when the lecture actually getting started, because these settings and everything will be in a part of the recording, and it's a little bit boring to see that. Okay, do you see anything? Do you see anything different in me? Correct. Hair is different. Anything else? Am I like a little bit more muscular than usually? Correct. That is correct. Okay, more. Anything more? Still, is that it? So I'm just more handsome than usually. I'm stronger than usually. I'm younger than usually. Anything else? And I noticed, you guys are not looking for any like good grades for this class or anything like that. You just say it because you feel so, right? Okay, but anything else? Headset.
Oh, you don't have.
I don't have a headset. Yeah, the headset is missing. Okay, so I noticed that you guys have not really put much of an effort to my haircut or anything like that, because you didn't notice they have missing headset. But I got the new gadgets, I got the new toy, and the new toy is a wireless mic. Every year I do something to improve my YouTube streaming quality. So it was a couple of years back I got this one, green screen, and this year is this one, new mic system. This is what I learned so far. I got it last week, Thursday. I learned that my voice quality is much better than previously, and the quality of my stories is improved. Look at that. Amazing mic. Really is amazing mic. But that's what's being told to me. I don't know if this is true or not, but we can figure out this later during today's lecture. Right. So we're here in lecture ID 11. As we discussed just before we get started, so we are approaching the end of the class, end of the entire course. And what follows after this week lecture is going to be visiting lecture and the summary. Summary about the stuff that you're expected to see in our next midterm exam. Next midterm exam, by the way, is something that we should discuss a little bit about the practicalities, because it's possible that we are able to cover all the all the theoretical aspects by next week. So would you like to make this next midterm exam to be earlier than originally planned, or would you like to keep it where it is planned to be? How you want to go? Before you answering that, please keep in mind this. You might think that, okay, everything is going to be so pleasant and nice before the Christmas because I have plenty of time before the Christmas, and you definitely don't, because all the deadlines are just before the exam, before the Christmas. There's all the other examinations and midterms just before the Christmas. So Christmas is the most stressful time ever. So what do you guys think? So now your answer.
Keep it in my opinion.
So keep where it is.
Yeah.
Keep where it is.
We can make a WhatsApp post.
Yeah.
So is what? So WhatsApp is saying what is what?
The poll and we can
Okay.
results out between the class.
All right. What about this? Because I'm so impressed about what you mentioned about my haircut and appearance and stuff like that. What about this? That you have 2 weeks time to do the exam. So you have more flexibility than usually. So we can get started 1 week ahead, and then the usual week, and 2 attempts. How that sounds? Is that the best solution? Okay, so that's the way to go. So we're gonna have we're gonna put the exam on in week 13, whatever the week that it is. I'm not even sure what week that it is. So the exam will be open. So what the WhatsApp community is saying.
It's competition.
So it's not the cream.
6 votes for early and 5 votes for regular time.
So that few participants in WhatsApp community.
Like start increasing.
Okay, all right. Okay, but what about this one? There's a 2 weeks time to do the exam. 2 attempts, highest will be accounted. So would that be okay way to go? All right. Okay, so I'm sure that's going to be the winning option for sure.
Yes, that's now we are leading.
Okay, so that is the one that is leading.
Yeah,
Okay, very good.
20 to 9.
So 22 answers.
20 answers for the early exam and 9 answers for the regular time.
Okay, all right. So is it? So somebody's just keep on clicking this option. All right, I see. Okay, so it's not that advanced that my Socrative in-class quiz system. Okay, all right. But anyway, so what follows is that we're going to have this visiting lecture, and this covers a little bit about this artificial intelligence, a little bit. But the real part about artificial intelligence and mechanical engineering will be offered to you in a class entitled Simulation Laboratory Course. There is a total of 4 weeks, or is it 3 weeks, that is all about how you can make a use of large language models, how you can use data-driven models, data-based models, how you can play with the different kind of modern technologies. This part of the course can be considered like something like official cheating part of the course, because we are solving these basic questions, basic problems in mechanical engineering using large language models and data-driven models. And that's quite educational. I'm sure you guys already are familiar with that, but we're using different kind of the large language models, including the GPT-4all, which is like a local large language models that will be installed these university computers. So that's quite a bit of fun. So I recommend to participate, because like mentioned earlier, this course is, in my opinion, which is not biased at all, but in my opinion, this is the best course that this university can offer to you. Number 1. Okay. All right. Now, any other practical matters to discuss? Okay. So let's wrap up the hydraulic components, and then we're going to move on to flexible bodies. Flexible bodies is going to be overview. I'm not expecting you to understand the details of the flexible bodies, because that particular field is very big. Multi-body system dynamics and simulation have multiple different sub-areas. And one of the big ones is called flexible multi-body dynamics, which is an area where you can take a body deformation into account. And there's a lot of different methods how that can be conducted in practice. We're going to learn 2 of them today, but not in a detail, but just like a little bit of an overview. Okay, this is what is possible, and this is what you can do if you wanted to model the deformation of a body. Okay, but before that, let's get started by summarizing what we discussed a week ago. So a week ago, we discussed about semi-empirical modeling approach. The semi-empirical modeling approach makes a use of analytical equations and experiments. And it kind of meets in the middle. So it's taking the analytical equations and expressing them in a format that unknown parameters, all of them, can be obtained from manufacturer's catalog. So it's a pretty simple concept that all becomes clear when we look at the throttle valve the one that it is in this slide. You know, the throttle valve, the analytical equation can be put it in a writing like this. So I have here discharge coefficient, I have here pi, I have a diameter of the throttle, and then I have a density of the fluid. All these unknown parameters will be combined and expressed as a semi-empirical parameter. This is the one that you can get directly from manufacturer's catalog. This is pretty handy technique because now, first of all, the number of unknown parameters will go down. And finally, you have a tool to make a proper interpretation how to get these parameters from manufacturer's catalog. The father figure behind, you still remember that? That is Heikki. So make sure that next time you see Heikki, you need to salute. And say, what about the king of the semi-empirical modeling method? How are you doing today? Okay. All right. So then we discuss about other components than a throttle valve. So the modeling of components consists of 2 steps. First step is that we need to understand where is the moving component, where that is located at. And the moving component is very conventional way in a hydraulics. An example is a direction valve where there's a spool that is traveling back and forth because of the magnetic forces. There are other forces that is also applying this spool, but typically it's assumed that the magnetic forces are big enough that they can compensate the other forces like pressure forces and flow forces, and that's typically is the case. So modern direction valves are designed in a way that magnetic forces are big enough such that whatever position you desire to have, the valve actually can receive or can get this position like no problem whatsoever. Okay, 2 steps. First, you need to know where the moving component is located at. And here, the moving component is this one, this spool. The spool is traveling back and forth. And when it is traveling back and forth, it is closing and opening the different connection possibilities. And motion of the spool can be modeled by using a simple first-order delay equation. This is nothing but the delay equation, introducing the inertia of the spool, because the spool is not very heavy, but still is having the something other than the 0 mass. And because of the mass, there's an inertia that is not allowed to this particular spool to move from one very short period of time to one location to another. But it comes with a certain delay. The delay is introduced by this equation. What do we have in this equation? So we have here input signal that is coming from control algorithm. It may be coming from the joystick that is operated by human. Those are the typical possibilities. And then I have the pool position here. U dot is here, this is U. And then this is something that is called time constant. Time constant defines how fast you can move from one location to another. This is almost like what's the relationship between the magnetic forces and the spool weight, spool inertia. Okay? Now you have 3 different scenarios depending how you're moving your spool. If you're moving spool to left side, this is going to be your scenarios. And look at this. So we are assuming all the time that the flow through the component is a turbulent flow. How I know that? I know that because the pressure difference is under the square root. So pressure difference and the flow rate, which is our basic primary quantities we are interested in, they are quadratically related. And then comes spool position, and then the semi-empirical parameter that tells me how big is the valve, what's the size of the valve. This one here, sign, is just taking care of that there is a possibility that the flow can travel opposite direction. It's possible if something is off in your hydraulic circuit. All right, so this is the first scenario. Second scenario is that nothing is traveling whatsoever, so no flow whatsoever. And then if you move your spool in the right side, these are the connections. Okay, then we learn about big promise, which is called digital hydraulics. Digital hydraulics takes this moving component spool away and replace the spool by multiple on-off valves. And these on-off valves can be on or off. So they have no opportunities between these two extremes. So they're either fully closed or fully open. And that's it. These are the two possibilities. So it's not working in the same way that the spool, which can have pretty much any direction, any position you want. So what's the big deal? The big deal is this, that there is this possibility to use this digital technology all the way in a pump. And you can make a signal to pump, typically a piston pump, and make a decision whether or not you put extra into your system or not. Today we're going to discuss more about the pump technologies and pumps, so you're going to learn that a little later. And then, it says that there is no leakage, which is true because there's no leakage over the spool. That's, of course, is a possibility. And there's this biggest thing is that there's a possibility of a bit more efficient energy consumption. That's a big deal, of course, because the hydraulics is typically based on pressure losses. The control is pressure lossing. Pressure loss is equal to energy loss. And that's we don't like in a modern society anymore. It was not a big problem a little while ago. So, but now it is a big problem. Okay, anyway, so this is what we learned. Today we're going to discuss a little more about that. Pressure relief valve will be left to you as a reading assignment because this is painful, complicated component that I'm not going to ask in a written midterm exam. Okay, not in a midterm exam, but if you choose to go to a written exam, questions are like, derive me the pressure relief valve equation starting from the Big Bang. And it's going to be so difficult that none of you will pass this exam. So please take the midterm exam opportunity because the final exam, you will not survive. There is no way to survive. All right, okay, but let's take a look at this. So what's the big deal? So this is how the pressure relief valve look like. Okay, and of course, this the drawing symbol for this component is like this. Oh, I'm sorry. So it's a box, and then I have here an arrow. This is where the line is connected. This could come from the pump, for example. This line is connected to tank. And then there's a spring. And then there's a pilot drilling here. This is a pilot drilling here. And what happens here in reality is that this spool, this is a moving component this time. This spool moves up and down. And when it moves down, it closes this connection here. And it's going to be the operation condition like shown here. So then there's no flow whatsoever. But what happens when there's no flow? This pressure here started to increase. Because particularly if the pump is something that is keep on producing the energy in the system, the pressure increases and increases all the time in this particular location. Now the pressure started to increase. Then the pressure here, I don't know if you guys can see my writing, but the pressure that is pushed this downwards and upwards, they will compensate each other. This is going to introduce no forces whatsoever. You see that? But then because of this pilot drilling here, the flow and the pressure can apply in this piston area or this spool area as well. It's not going to be the same than this one because there is a throttle here inside, but it's a little less than that. But because of this pressure, it started to pushing this upwards. And then there is one more force that is applying in the system, which is a pre-tension spring here. And pre-tension spring tried to put it downwards. Now this force, pressure multiplied by corresponding cross-section area against pre-tension spring. And these are battle. That's where the battle is set. And as soon as the pressure corresponding the cross-section area becomes to be bigger than the pre-tension spring, that's when the valve, the spool, is moving upwards and the flow started to go from pump to the tank. Okay, but this is, by the way, this kind of the design used to be pretty standard design, at least in industrial applications a little while ago. How you like about the design? There's a pump that takes the fluid from the tank, pressurize it, put it in a system, and if it is not needed, pressure relief valve, put it back to the tank. you circulate the flow, and usually you need to get the cooler of some kind. So this is typical example about case where you're wasting awful lot of energy, a lot of energy. So this kind of design is not that much in a fashion. It's still a little bit in fashion, because alternatives where you're actually controlling the pump is something that have a little bit of reputation of not being that reliable. Okay, this was when I was a younger, I'm not saying young, but younger a little while ago. It was still not considered as reliable as the pump that is keep on producing the pressure, fixed volume pump, not the variable volume pump. All right, anyway, so this is the scenario. The model here consists of this kind of semi-empirical model. So the flow through this pressure relief valve can be component. Oh, I'm sorry, this is not the semi-empirical model, because I have here discharge coefficient, I have here the diameter, I have X here, I have all the components. X you can solve by this equilibrium equation. But you understand that this requires a lot of parameters. Many of them you just cannot get an access to. There's no way you can get an access to. So what Heikki discovered, that this equation, which is pretty complicated, can be replaced by this first order differential equation. You solve the K from this equation. You put is it this any better? I think the voice is back.
Yeah.
But now it's like super loud. Is it a little too loud?
No, I just
Yeah, but I think that I'm still too loud because I see that I'm red all the time. So it's oh, you don't even see this. This is my OBS system. Are you guys, by the way, using OBS when you do your YouTube videos or no? You don't do YouTube. Okay. Okay. What about the WhatsApp community? Are they saying that they're happy again? They're happy. Okay, good. Can you please take a look at if there's another problem? I think I made a mistakes in my settings because the new gadget. So I select a little bit of incorrect channel and that somehow got stuck. Okay, should be fine now because the audio input capture is good. All right, let me take myself back here. Okay, so online participants, there was a best joke ever. You just miss it. People here in audio, they were like laughing, like they thought that they're gonna die because it was so hilarious. You miss it. And because of my memory is strong but short, I don't remember the joke anymore. So we're gonna just go. Okay. What's this? All right. So hydraulic cylinder. So this is a component that converts hydraulic pressure to mechanical force. Two-way cylinder like this depicted in this slide produce the force in such the way that there are two pressures that are affecting the amount of force produced by cylinder. And these forces are pressure that is applying in a piston side. Pressure in the piston side multiplied by corresponding cross-section area is the one that is pushing cylinder, or let's say cylinder rod in right side direction. Then there's another force that is pushing this in opposite direction, which is going to be the pressure applying in a piston rod direction, this direction, multiplied by corresponding cross-section area. This cross-section area is smaller than this one because of the piston rod itself. So it's a same size minus the piston rod cross-section area. Okay, so this is the force produced. There's only one more component that is a little bit unknown, and that is a friction component. Friction is because of there are sealings here in the piston to prevent the flow to travel from one chamber to another. There is another sealings to prevent oil to come off from the cylinder. And because of the sealings, there is a friction. Friction is, well, let's put it this other way. Efficiency of hydraulic cylinder, I mean, how much force is coming out is dominated clearly by these two components. So it's dominated by hydraulic pressure. This is percentage-wise typically, let's say 5%, 10% max. So efficiency, if we want to explain it this way, of the hydraulic circuit is like 95%, which is pretty good efficiency. This 5% is still important because this is the one that introduced the damping to hydraulic system. There's no other clear damping mechanism or damping components in hydraulics other than friction that is coming from hydraulic cylinder. And this is when you see the pressure, for example, in your simulation model to go like this, damp down, this is because of this friction. If you don't have a friction, it's never going to damp down. It's going to be like this forever, pretty much like this. There may be numerical damping, but that's a little bit artificial. Okay, the only component unclear is a friction. And friction behaves in a way that we call, that I mentioned last week already, as a stick-slip friction. So this is sometimes described like a beam that is, well, let's say the beams, there's like a surface, rigid surface here, and then there is a plate that you move this direction. And what is between the plate and the surface are like beams, deformable beams. And what happens when you do this, these beams are deforming and until they reach certain configuration, and then they started to slide and they come back to this original configuration. So this behavior, when you look at the friction force as a function of friction, I mean velocity, not the friction velocity, but the velocity between these two objects, can be described such that the friction, when the velocity is very low, is having the negative slope. So it's moving downwards, that the friction is going less than it was in a static configuration. This is a little bit against the common sense, because I'm sure you have typically seen the friction that is increasing as a function of velocity. This is a very typical scenario, but this kind of scenario is because of this kind of like deformable bristles. And because of this behavior, it first comes down, and when you're still increasing the velocity, then it slowly started to go up again. This is called stick-slip. Sticking, slipping, sticking, slipping. And this is what makes that kind of the noise that you can hear all over. And I think this table will be behaving like a stick-slip system. If I'm going to move this table back and forth, you're going to hear this noise, like or like, let's hear it. So I don't need to pretend it. Let's hear it. If we can hear it. You hear it? Hear it? So where this noise is coming from? Because it's sticking, and then it is slipping, sticking, slipping, and that happens in this frequency. This frequency, pretty high frequency. Oh, okay. So this demonstration was so powerful that even the camera went off. So is it on my back?
Yeah.
Oh my God! Stick-slip friction is so powerful that it can turn the camera like upside down. I have never really thought about this before, but amazing, amazing stuff. Okay, this is stick-slip. How we can model? Of course, there's a, if you look at the friction models, there's a lot of different ways that the friction can be modeled. Columnar friction is like the simplest, which is like, very, very simplified way to model the friction. But then there's a bit more advanced, like Lucre friction model. Lucre friction model is already taking this phenomena, stick-slip, into account. Another simple thing you can do is to have like a curve fitting. So what is highly recommended, or where it's often used too, is that you have a curve based on polynomials such that when the velocity is zero, you still need to put this to be as a zero force, because otherwise you have a discontinuity problem. But then it rapidly increases here, kind of describing the static friction. And then the curve, this polynomial curve, will go down and start to increase. And this particular behavior is the stick-slip behavior. And then it's going to be, another direction is going to be symmetric like this. So this kind of curve is something that is typically representing the measurements as shown here. And then, efficiency is just telling you how well they are following this particular measurement curve. And of course, this is a net force. And this is this curve that I just described here. Okay, makes sense? Yes, sir. Okay, so the curve, the curve would be, in best possible scenario, would be like, let me see if I can take these drawings away. Oh, just a second, I will be putting this back. All right, so behavior here is a empty space. This is this x-axis, this axis is velocity, and this is friction force. And this behavior based on the measurements was such that there's a pretty high static friction. And whatever this velocity is non-zero, the friction will go down. This is this slipping part, and then it will have like the lowest value has started to increase a little bit like this. This is what we would like to do, but we cannot do this. And we cannot do this because the problem is that because this is symmetric, when the velocity is negative, this is going to look like this. And this is a big problem because, in a simulation, if you have some kind of like a package here standing in the floor, and you move this up and down, left and right, your velocity is positive and negative. You need to cross this particular area. When you do this with this heavy discontinuity, your simulation model will say, this is it. I'm unable to understand how this behaves. So what you need to do, you need to fool your simulation model and say, hey, take it easy, because when you're having the very small velocity, you can actually cross it through the origin like this. And this is the curve. This kind of what forces it to travel through the origin is needed, because otherwise there will be a discontinuity. Discontinuity is something that the simulation hates the most. They really hate it. They cannot get along. So it's absolutely impossible that you have a discontinuities. No, it's still possible, but let's say that there is a hard thing to deal with if there's a discontinuities and simulation model. I said this incorrectly, because there are cases that you can actually, there's a branch of dynamics which is called non-smooth dynamics. Non-smooth dynamics is something that you can take these discontinuities easily into account, but that's a family that is something that most of the doctoral students in each of the the ones that are specialized to simulation, they are not really familiar with. So this is quite special technique. But some of the game engines use the technology that is based on non-smooth dynamics. So what the heck is this thing? Guess where you can learn this? Correct. Simulation laboratory course. Like how to live a good life. Guess where you can learn that? Simulation laboratory course. Okay, enough about marketing, but is this clear now? Clear. Okay, very good. Very, very good. We were here. Pump is the last component left. What the pump is doing, what we are thinking pump to do is producing flow rate. This is a little bit of chicken egg thing, because the flow rate, when you're restricting the flow rate, what that's gonna give it to you, that's gonna be the pressure. But we're always assuming that the pump will produce the flow that is coming out from the pump. And when you're not allowing the flow go freely, you're restricting it, you're gonna get a pressure. That's the mechanism how it is thought to behave, because it's like the mechanism to produce flow to travel forward. And how are these mechanisms? Of course, there is many different ways how you can make it happen, but the standard ways is like a piston pump, but there could be other ways that you can produce the flow to travel forward too. But here it is. So in a modeling perspective, we are assuming flow to come from the pump. And then it comes to the first volume. And if the incoming flow rate is more than outgoing flow rate, it started to produce the pressure that is increasing until they level off. This is how we thought things to happen. Now, pump technology is something that we have two basic choices: fixed volume pump or variable volume pump. Fixed volume pump is something that keep on producing the flow rate, this guy here, regardless of its need. Sometimes, you can consider this as a flow to the system, and it's keep on doing that, even though that is not necessarily needed in a system. Then you need to get this pressure relief valve to take excessive amount of energy from the system. You put excessive amount of energy back in the tank, where the pump is sucking it, and put it in a system. And again, if it is not needed, then it's going to be circulated like no limit. Because it's circulating that much, you even have to have a cooling system, some kind, to make sure that the fluid itself is not heating too much. Okay, so fixed volume pump. That is a simple model, because pretty kind of like what we need to know is that we need to know how much is the power of the motor that is running the system. So typically, these are, in industrial applications, these are operated by electric pump. As you know, pretty much the capabilities of the motor, how is the max power that they can produce. If it is a diesel engine, you know that too. Diesel engine typically is designed to be such that in a mobile machinery, the diesel engine is running with a constant RPM. It's just having the constant RPM. You don't, like, even when you pushing the pedal, the RPM stays where it is designed to be. It's just controlling this in a little bit another way. Okay. Okay, this is not entirely true. There's a possibility to increase the RPM as well, but in a standard way, there's a constant RPM to be operated in an optimal range, and that's how it's operating. Fixed volume pump works like this. You have this pressure equation, power equation to be more specific. Power is equal to the flow multiplied by pressure. Now the flow is the one that we are interested in, so we would like to solve this guy out from this equation. Okay, that's it. So we can solve it like this. Mechanical efficiency needs to be taken into account, which is pretty good too. So this is something that ranges 0.9 to 0.8 to 0.99, something like that region. And that's it. But there is also this maximum, like physical dimensions of the pump, you cannot exceed that. So how you do the model, you do it in a way that you computed this one, this numerical value, and this numerical value, and then you select the one that is giving you the lower value. That's it. And then you're good to go. Pretty simple model, isn't it? What about the alternative? What if there is some kind of like a control mechanism, something that you're producing the flow rate depending how much it is needed? Now, here comes a wide variety of applications and wide variety of ways you can do this control. You can have the controlling such that you're measuring the pressure right after the pump. Right after the pump, you're controlling the flow rate based on how is the pressure right after the pump. And if you are happy with how much is the pressure right after the pump, you're reducing the flow rate. You put your energy production to be lower than it otherwise would be. Then there's a way more clever systems where you're actually monitoring how is the pressure in multiple different locations in your hydraulic circuit, and then you see if there is the pressure that is something that you feel that. Let me put it that way. So you're monitoring the pressures in multiple locations in your hydraulic circuit. This monitoring is typically right next to the actuators. You're selecting the highest out from the many, and then you're making sure that there is this with respect to the pressure that is somewhat close is always having some kind of reference. So there's always a reserve available for you. And the reserve is something that is constant. So if the max somewhere near to your actuator is 100 bar, you make sure that right after the pump, the pressure available is, like if your reserve is 20 bars, so it's 120 bar. If your pressure in your hydraulic cylinder is 50 bar, then you are having to reserve the pressure right after the pump, which is 70 bar. So that's how it works. And this is another way to control the flow rate. You got it? No, you guys are lying. You're kind of hoping that, let's have a break. And in a break, I'm thinking like, I'm going to Google, like, what the heck is this load sensing and the pressure, these variable volume pumps. This one here, what I just mentioned, where you're monitoring the pressure right after the pump, is a constant pressure control. When you're monitoring the pressure in multiple locations, typically close to the actuators, this is called load sensing. So you're sensing what's the current load. You make sure that there's a reserve available for you any given time. There's a fantastic YouTube video that we are about to take a look that is clearing the issue. This one. Oh, no, thanks. Is there any way that I can? No. What about the online participants? Can they hear this or they can? Yeah, but how can I put I think that I need to put the volume up. Hold on. Our speakers will go here. Okay, let me try it. No, you don't see it. Let me try it like this.
Today, together with our partners and customers in 6 countries, we are recreating logistics. We are here to serve, to care for the people, and for the future generations. Times change. Mission remains.
Welcome to Lunchbox Sessions, bite-sized industrial training.
Hey, it's Carl here from LunchboxSessions.com. This will be a brief introduction to load sensing pumps, sometimes referred to as flow compensating. Our pump still has that very heavy spring, that major adjustment called the pressure compensator or the pressure cutoff for when we hit that really high top end pressure to make sure our system is protected. But it also has a weaker spring called the load sensing adjustment or the flow compensator. And that flow compensator is receiving information, feedback if you will, coming directly from the load, our cylinder, which right now is working at 300 psi. That's the pressure it takes to lift the cylinder and rod. And that 300 psi is being fed back to the controller and giving that spring a boost. I could tell that the spring is actually set to 300 psi. How did I figure that out? I figured that out because our pump outlet pressure is set at 600. So it's taking 300 from the load and adding it to the 300 spring setting. And those two pressures add together, those two forces add together to give us our regulated pump outlet pressure of 600 psi. This is different from a pressure compensated pump, which might be set at, say, 2000 psi at all times, and therefore using a lot more input energy. So in this particular case, we've got a pump that sets its outlet pressure just slightly higher than what's needed by the load. We've got to have some kind of a flow controlling device in there. This is our needle valve that's being used to set our desired cylinder stroke speed. But let's have a look at what happens when I add a brick to the brick stacker. Our load pressure has gone up to 600. But what happened to our pump outlet pressure? Somehow it automatically adjusted from 600 up to 900. What we're finding out is that we're always maintaining a 300 psi pressure differential, sometimes referred to as a 300 psi margin pressure when we're referring to load sense systems. Let's add one more brick, and this time watch the delta P gauge. The delta P gauge fluctuates for a brief fraction of a second, but quickly we find it returns to 300 psi, and we never really noticed any change in speed at the cylinder. The cylinder just kept moving nice and steady, and our pump found out that it needed to increase the outlet pressure setting automatically. So what we found out is we can have a pump that is set at a pressure that's just a little higher than what's needed at the load, instead of being always at the pressure cutoff pressure, which could be considerably higher. And because we know we want steady speeds to our hydraulic cylinder, we don't wish to see any fluctuation in speed. Every time we take a brick off the stack, or every time we add a brick to the stack, the pump knows to adjust itself accordingly so that the flow rate through the needle valve doesn't change. That's the nature of a load sense system, and that's a brief introduction to load sense pumps.
Okay, pretty clever. And what if it's going to be, it can come from the multiple locations. So here was a one location. So actually the idea is that you can have a multiple actuators, each one of them are monitored. And you look at the highest pressure and make sure that there's always a reserve available. So you can still move in the direction you want. So that's the idea. So that's pretty much the best you can get from the mobile machinery today, load sensing pumps. But this was something that you guys were already aware of, right? Because Heikki, I'm sure he explained this story multiple times to you already. Kind of, in his own ways. Okay, very good. All right, so I know we need to have a break, and we will do so momentarily. So let me put this back on. And let me just wrap up the case about the pumps, and then we get to go. Again, here is like the case that you're checking in this kind of the system, you're checking the two different locations, the pressure, and then you're selecting the highest, and the highest is the one that is you're using to controlling your load sensing pump. Parameter is needed because remember, the model that we're using is this one. We need to get this time constant, so we need to get that from this this K parameter. We can get it from the manufacturer's catalog. Details, you need to take a look at my lecture notes. But again, this is a semi-empirical modeling approach where the unknown parameters you can get from the manufacturer's catalog. This is it. I have 2 in-class quizzes today. First one is this. In hydraulic model, in a modeling, what is that we are assuming pump to produce? Pressure, oil flow, temperature, voltage. One only is correct, but which one is correct? In-class quiz is on. So before you head into your break, well-deserved break, why don't you answer to this in-class quiz? So is it going to be the pressure, flow, temperature, voltage? In a modeling, when we do the model, which out of the 4 is correct? What is a WhatsApp community saying? Are they voting for temperature or voltage? The voltage? Well, B, oil flow. Okay. All right. So once you're done, then you can have your, how much we need today? 5 minutes? Is 5 minutes okay? Five. That was a question. 5 minutes, is that okay? Thanks God I don't have any more complicated questions than that. Okay. Okay, 5 minutes. So once you're back, we're going to take a look at these in-class quizzes. Now let me explain in what follows. Then we're going to take a look at this particular example. So we look how you can create the model for this example hydraulic circuit. And once we're done with that, then we're going to move on to flexible bodies. Flexible bodies, like I say, it's going to be an overview, something that is in a level good you to be aware of. But are you guys familiar with the technique that is called, not the technique, but the method that is called finite element method? Finite element method, okay? So that is when you're discretizing your structure to small elements. The small elements are connected together in nodal locations, nodes. You're solving the nodal degrees of freedom. Okay, good, because this is a method we are not using. No, we're using that, but we're using that with a certain kind of special technique, which is called modal reduction technique. Okay, all right, but let's have a 5 minutes break and then come back. Okay. Did I got any comments about the quality of voice? Is it any better than?
Yeah, the first they say the voice is better now.
Better now.
The first
First, they say you were looking smart.
yeah.
Oh yeah, but that.
Yeah,
So each one of them would like to score a 5 out of 5 from this class, I think.
the second one, the voice is better.
Yeah, I think it is better.
They say no voice.
No voice. Yeah. And it's kind of stupid to wear this headset when you are middle of the people. That's another thing that I don't like it so much. Yeah. Okay, so it is an improvement then. I just don't know how much this battery. Oh, they say battery is still okay, so I think it can easily handle this kind of like 2 hours lecture. Yeah, nice. Like that?
DJI.
I don't know what brand is this.
Yeah, you can see from your mic.
From my mic? I don't know. Can you read this?
Yeah, it's a DJI.
Is it? Is that a well-known brand?
Yeah, whole drone.
DJ. Oh yeah, DJI. Yeah, you're right. It is a DJI.
They're making drones and those kind of things. Film. Like this.
Okay. This was recommended by people that are doing these YouTube videos to university channel.
And it's pretty expensive.
This I don't know because I got through this guy, so I don't know how much this cost. Yeah. But
Is that me too?
I don't know what that is, but I have like 2 mics. So I have another mic which is not with me, but I can use 2 mics. I think this is perfect for interviews. So you have 1 mic for yourself, another one.
27 in Gigante.
How much?
227 in Gigante.
So it's not that affordable. But I've been trying so many different ways to do it. You know, some years back I had like wired mic. Very bad idea. Very, very bad idea. And then this different kind of their low quality wireless wasn't very good idea either, because this wireless with the low quality, they don't work. They are just not willing to collaborate. And now this seems to be finally the way to go. This is a simple settings because the only thing you need to do is just connect and go.
Some other brand called Raw.
Yeah, I think it is a good brand too. Good one. It's a well-known brand.
Same price.
Same price. Yeah, I just kind of started to run out of the ideas. Like, what would be the next step to take my YouTube streaming to another level? Don't know, but don't say quality because this is something we are not going to touch. Content. I mean, don't say content. The content could be a bit better.
But you don't use any markers or something because.
Markers?
Like glass.
Oh yeah. That's gonna be. You know, I know this technology. I'm aware of this thing.
Can be like I know that sometimes it's getting not messy.
Yeah, this is simply because you know, when I do this writing to this screen, it's there's not much space, and that makes it difficult. But I know this technology. This is called like Lightboard or something like that. And a friend of mine is very into this technology, and he created the system that when he's walking around in a classroom, the camera is following you. But I cannot use that because green screen.
Yeah.
And I tried a couple of years back. I tried to this background removal system. That's very, very bad because my computer is not strong enough to do that in a proper way. So it was causing a major like problems in my streaming itself. Okay. All right, guys. So let's take a look at the in-class quiz. And this one. No, this one. What? Where is my... and my Socrative is not... Here it is. Squeeze.
We can't see that.
Yeah, you cannot see this, but I'm very, very confused because Socrative is supposed to be on, but how can I see... how can I see the... How can I get into this activity that I'm currently busy with? Launch, because this is already launched. I lost this because this is the only window that I have, correct? Yeah, this is the only window that I have. launch reports live. Okay, this is live. Oh, here it is. So it was simple like this. Okay, all right, I'm very proud of you. I need to say this. I'm very, very proud of you, not because you're scoring so well in in-class quizzes, but more because of the number of participants haven't really dropped significantly. We still have 127 participants, which is a really good number, really good number. Okay, is it going to be or is it not? 100%. Yes, it is. Yes, it is 100% because we've been talking so much about, how we're producing the flow rate. It's very good, very good. Not pressure, but the flow. Chicken egg. And we decided that it needs to be flow that is coming first. And then if you're reducing the flow rate, then you get the pressure. Okay. Okay, then there's going to be another in-class quiz, more difficult than this one. By the way, I need to tell you this. I called this rector again once, this was a couple of weeks back. So we called the rector and I called him again and I asked, like, am I now fired? And he said that, yeah, next time you do it, you are. Consider yourself to pack your stuff and leave. No, he was like, it was a good stuff and he kind of liked this kind of thing. But this is our rector. Usual rector, you do the call like that, you can consider yourself as a, between the tops. Immediately, because this job is gonna be over, and for sure the usual rector let you go if you do something like that. Okay, all right. So this is this is not mechanism. This is a hydraulic circuit we're gonna model. So what are the steps? Again, we're gonna follow the certain steps, and automatically we're gonna get equations we need. Number one, discretization, idealization. So we need to figure out where are the locations that the pressure need to be computed. Here is an obvious thing to select the way I'm selecting it here. So if there is a position of this, if there's a direction valve and the direction valve is connected to throttle valve, this is definitely one area you need to compute the pressure. Why? Because throttle, this component, will introduce the pressure loss. There's another volume that you need to compute the pressure, which is right after the throttle valve. Way back, when you look at the piston rod side, there's only one volume that needs to be considered. Now comes the very important thing. Look at another symbols that I added here in this figure. I added the symbol about the positive flow rate. You can do any way you want. You can put this any direction you want. But what seems to be very, very complicated to accomplish is to be consistent. So once you make this kind of the drawing, you just need to understand that, for example, here, when the piston is moving this direction, which is considered positive direction, the flow is coming in to this P3 and is leaving because of this one. That's how you can select the right plus and minuses. Okay, so this is a idealization. The next, let's figure out how big are the volumes. First volume is very simple. It is the size of the hose, which is a hose line connecting the direction valve and the throttle valve. Then the next volume is a hose that is connected from throttle valve to cylinder plus cylinder valve. Then the third one is a hose line plus area that is associated to piston rod area. Okay, that's it. That was done with the step number 2. Step number 3, bulk moduluses. How many bulk moduluses I need? 3, because I have 3 different volumes. So it's not enough to compute one and say, okay, this is it for each of the 3 volumes. Because each of the 3 volumes, you will get a little bit of different values. And you need to do it separately to ensure that the accuracy is in desired level. So this is how you compute the first one. So it's only the bulk modulus of the fluid and the hose, nothing else. And the same, the size of this is the same all the time. In the second one is a volume in the fluid, container that is associated to hose, and the container, this is the hose, by the way, and container that is a hydraulic cylinder, still container. Third one, fluid, cylinder, hose. So I'm assuming that there's no dissolved air, which is not necessarily the accurate assumption, but that's our assumption I did. Step number 4, the most critical one. So now we are actually forming this first order differential equation to compute the pressures. And a seemingly simple procedure to follow practically is more complicated than you think it is. Okay, let's get started from the P2. P2. This flow here is assumed to come into this volume. So it must have a positive sign. This one here is having the plus because of this arrow is coming in. Okay, makes sense. When the piston movement upwards direction is considered to be positive movement, this piston motion is taking a flow off from this particular volume. That's why this one here is minus here. Rest, this was already computed. This was already computed. The only thing we're doing is that now we figure out the proper plus and minuses. Clear how I did the volume 2. Was that clear? Absolutely clear. Okay, 3. This was computed earlier. This was computed earlier. This is bringing volume in, correct? And this is taking volume off. That's why the minus sign here. Now, based on this, can you tell me how it's going to be this one? Which one is in and which one is out? Okay, tell me. These are the options. Options are that this is QI is, one is in, 2 is out. Then the second one is both are in. Then the first one is out. Second one is in. And then both are out. One only is correct. But which one is correct? Hold on. So it's going to be this is the last in class quiz of sorry guys. No, it's not coming back. So let me try one more time. Yep, here it's coming back. Okay, this is not very informative for you because you need to see these are the options. So let me try to make this a little bigger so you can see this clearly. So these are the options. Again, take a look at the arrows, how I'm defining the positive flow direction. 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 Okay, is it clear? So what is that the WhatsApp community is saying? They're saying A. Interesting. Okay. Okay, let me take a look how many answers we got so far. So how many answers we were able to collect. Okay, so we are a little bit like, let's say halfway done. Now we have 65 answers only. So please cast your vote. Okay. Success rate is how much? 93. I'm with you. 93. So 2 of us is a 93. What about the rest? 90. 90. Yeah, 100. Yeah, that's this is what that's what is called can-do attitude. You know how much we value the can-do attitude in this course? We value that a lot. We value a lot. A lot. Okay, we got 100. So the rest, last ones, please enter your answer when we are good to go, because we still have a few more steps before we are ready to close 104, 105. Okay, now the last ones are entering. $108. Okay, what do you guys say? Is this it? This is it. So we are not going to collect any more answers. So it's 108, 110. 110 is good. Now we're going to close it. And the success rate today is 95. 95. That's not bad at all. That's very good. Okay, let me put myself back to the PowerPoint presentation. And then let's take a few more steps. Here it is. This is what we were looking for. This is a correct answer because this obviously is coming in. This is leaving. So that's why this is having the plus. That's why this is having the minus. So it's not randomly selected. Okay, valves and the flow rates. The valves having the pre-operation configurations depending on the spool position. This is what we discussed a week ago. And the throttle valve was something we discussed a week ago. So this is a copy-paste from the previous lecture. And the last thing, force produced. The force produced is very important because now we actually have a force that is somehow based on the reality. And I really don't appreciate much about these models that you have a very complicated mechanisms. You're guessing how much actuators are producing the forces because then you're guessing the responses too. I'm sure you understand that. Another way around. So if you have very accurate models about the actuators, but you're guessing how is a mechanism, that is equally low value for us. So this we need to follow something that is called equal accuracy modeling principle. Something like that. I don't know what is that, if there's any official name, but the actuators and the mechanical components have to have the same level of accuracy. Otherwise, it doesn't make much of a sense. Flexible bodies. Okay. So now I just say that the mechanism and the actuators need to be in the same level of accuracy. Sometimes what you need to do to increase the accuracy in what comes in a mechanical component is that you need to take a deformation into account. Or maybe you want to take a deformation into account because you are interested in about the strains and stresses. You understand that if you have rigid bodies, then the rigid bodies they don't deform, and because they don't deform, they don't have any deformation, and because of no deformation, there is no strains and there are no stresses, and you cannot get this quantity out from your model. Okay, how is it we can model the flexible bodies? Let's discuss this a little while. You know that I mentioned in the beginning of my class that we make this assumption about the rigid bodies. It is an assumption because every single body is a flexible body. But really the important question is that when the flexibility is significant enough, that is actually contributing to dynamic responses. Now this is not easy to answer. There are like some rules developed, but none of the rules are very good. This is more about not the common sense, but engineering sense to define when the deformation is really that significant that the deformation needs to be accounted. Then this is a big problem because we learned that rigid bodies consist of very high number of particles. Same is the case in deformable bodies. And in theory, each of the particles can move with respect to each other. And that will mean that to model something like that, there's going to be trillion degrees of freedom, which is computationally not possible to do. So we need to discretize, we need to make a decision. What are the different ways that the particles can move with respect to each other? And this is going to give us something that how many unknowns we're going to deal when we're going to modeling or when we're going to deal with the flexible bodies. Now, field of flexible body system dynamics can be categorized to two fields. There's like small deformation or large deformation. And what I'm about to tell you is that I'm going to shortly introduce you the method that is based on lump mass approach, which is not strictly speaking theory of flexible bodies, because this is based on rigid bodies. Between the rigid bodies, we're going to introduce symbols, spring elements, and dampers to describe something which is like seemingly deformable body. But then I'm going to introduce you another method, which is this floating film reference formulation. This is a method that is very good for deformation that is pretty small. flexible multi-body dynamics. I mean, the field can be categorized to two sub-areas, which is a large deformation and small deformation. But the difference is like how you are assuming the displacement and strain to be related. Okay, what is this? So is this. So if you have a cantilever beam like this, and you have a force in the free end of the cantilever beam. Okay, now what's going to happen because of the force? There's going to be deformation like this. So each point of the cantilever beam, I can compute how much it is deformed from the original configuration. This is called displacement. The displacement is a function of length of my cantilever beam. Because, here obviously displacement is less than here than it is here. So it's a function of where you look at it, this thing. But this is kind of the continuous function you can create. And now is a very important question because this displacement and strain are related. Where you relate them tells you whether or not you can take the large deformation into account. Most of the literature, and I'm sure everything you have learned so far, this relation is assumed to be linear. Something that you can compute the linear relations between the displacement and strain, which is okay, but limits yourself to the small deformation. Is that a big problem? Well, depending how you look at this thing, because here, like I described this cantilever beam, the deformation looks pretty good. It looks realistic. What do you think? This is how it deforms if you do this in a real life. Yes. Now you say yes. Yes. Okay. So what happens if I increasing the force here, if I could put more force in the system, and if I still have this assumption about the linear strain displacement relationship, then it started to look a little weird because what happens is this, the deformation is going to be like this. Free end of the cantilever beam remains in a line where it was in the original configuration. So it's not moving at all in a transverse direction, let's say longitudinal direction. And this is not what you can see in a reality. Or can you see the deformation like this in reality? No, you see the deformation like this. This is what you can see in a reality. And now the big difference is this. This free end is actually moving also in axial direction. To take that into account, you have to use nonlinear strain displacement relationship that complicates everything. Your life is going to be way more complicated than it was. That there's another, this is called geometrical nonlinearity. There's another source of nonlinearity, which is called material nonlinearity, which is common, it's not common in dynamic applications. And this material nonlinearity is a relation between the strain and stress. I'm sure you have seen these famous graphs about strain and stresses like this. In a steel material, they behave like this. There's a linear relation, and then it becomes to be nonlinear like this. So again, if you're really introducing a lot of force, there's going to be a lot of displacement, a lot of strains. You might travel all the way here. When that happens, when you take a force off, you're no longer coming where you start from, but you have a permanent deformation. This one here, when you're moving from this to this direction, is called material nonlinearity. Not common in a dynamic applications. Why not? Because it would be like a crane that you have a brand new crane, and then you put a load top of the crane, and you lift it, you put it back, and it's like this. Mm-hmm. This, you know what that is called? Bad design. It's because if the brand new crane is after first lift is already bended, customer is not going to be happy. It's going to call you and say, okay, I want to get the better product. Your product sucks big time because it's not able to handle the load like this much. And that's the case. So that's why this another nonlinearity is not very common, whereas this geometrical nonlinearity happens every now and then. Again, this is a mechanism. So you have a deformation, displacement, you compute the strain, then you compute stresses. You may be mostly interested about this one. In a design, if you know the stresses, this is very often used as a design parameter to figure out, because the stresses need to be below the certain value. Particularly if it is like dynamically loaded structures, which could be suffering from fatigue, you better know the stresses, and even you need to know the stress histories, how much the stress is changing as a function of time, because otherwise you may suffer from fatigue problems. We can get back to this fatigue a little later, not in this class, but in a class that is entitled, correct, laboratory course. You guessed it already, I guess. Okay, all right, so this is what I just explained to you. So this differentiates the flexible bodies, if it is small deformation or large deformation. Here, this is a linear strain displacement relationship. This is nonlinear. This looks okay, so I don't see this looking that bad, because that's pretty realistic. But the bigger the deformation, the more unrealistic it started to show. All right. So which one of this one is linear and which one is a nonlinear? They are not having that big of a difference, but you see the response-wise is a pretty significant difference. All right. So like I mentioned, there was a desire from student union to explain what is the research in LUT. And you look at the papers in the teams that are focusing on dynamics, including Jussi Sopanen's team. Most of the papers are related to area where they are developing the methods to describe these large deformations. There's a big, thick body of papers about how to make this kind of the models to be computationally efficient in multi-body frame. But this is how much we're going to touch that subject matter in this course. We're going to look at a bit more simplified ways to model the deformation. All right. But again, like what these research teams, what they wanted to do, they are not just happy to describe deformation of small deformation, like let's say the connection rod in a crankshaft mechanism, but they would like to be able to describe like a belt. And the belt is undergoing the large deformation. This is very challenging. And this is where the most of the methods that are developed are focused on clothes, cables, drapes, wire ropes, so on and so forth. Okay, but the methods that can describe, let's say, that are commonly used to describe the deformation, well, the methods are lump mass approach. Like I said, this is not strictly speaking based on the theory of flexible multi-body dynamics, because this is an extension of rigid bodies. And it works like this. You have original body, typically need to be beam-like body, because otherwise it's going to be really, really difficult to use. What you do then is that you take your beam-like body, you describe your beam-like body with a number of rigid bodies. They are still rigid bodies, and they have roughly the inertia properties of your original body. And then comes the magic component. A magic component is this: you're introducing spring elements to all the 6 degrees of freedom in spatial applications and 3 degrees of freedom in a planar application that introduce the forces between your rigid bodies. And because of these springs that are forces, is act like flexible body as a total. So now multiple bodies becomes to be one flexible body. That's the idea. Not used anymore. This is something that technique was very much in fashion a million years back, but not so much anymore. Because there's a big problem here, which is, you understand that you are having quite a bit of effort to compute multiple rigid bodies. And it really is a problematic because some of the springs here are pretty stiff, particularly the ones that are related to axial deformation. And for your information, simulation don't like the discontinuities, but it doesn't like another big problem, which is the natural frequencies spread around the different regions of frequencies. This is what the simulation always is struggling with. And it's like this. So if you have, let's say that you have, let's say that you have, again, this your cantilever beam, which is modeled by using these rigid bodies, spring elements between these rigid bodies. And then you have a force that is like not perpendicular with respect to structure, but a little bit other than perpendicular. So what happens is that, if you look at the response will be like something like this. The force is pushing this downwards, and I'm measuring the deformation downwards direction. But if you take a really close look about this, really magnifying a lot of this response here and make a big picture, you see that there is a vibration like this. The vibration like this is simply because of the axial springs are deforming. They are acting here. They are not making any difference in terms of the big picture. This is irrelevant. So it's something that you don't care at all, but the simulation, the integration time screen is able to recognize that, hey, wait a minute, there's something that is happening with the high frequency. And because it recognizes something like that, it is tuning its time step to match this very high frequency. And the computation is not going anywhere at all. So it's extremely slow computing. Okay, I'm cutting a lot of corners when I explain that, because there are ways to deal with the high frequencies and low frequencies in the same model. Yes, that is possible. You can use a different kind of numerical damping procedures, but as a rule of thumb, first thing you want to do is not to have a model where there's a high and low frequency in the same model. That's as a rule of thumb. Okay, so that's a method, and it can describe even this nonlinear strain displacement relationship, because each of these are linear systems, but when you keep on adding the linear systems, you can account certain level of nonlinear deformation. All right, so these are the examples. Cranes that are modeled a while ago, so they are not very big ones. So this is the one that is a cable structure. The cables is still being used. There are a better method for cables, but let's say a few years back, this was a standard method for cables. Now there's a better method available. You see, it looks pretty realistic. So these are these masses that are connected together via spring elements. All right, computationally expensive, can be applied for beam-like structures only. Damping models are not very advanced. Easy to implement, easy to use, simple theory. That's advantages and disadvantages. And now I know that we don't have that much time left, but let me introduce you this method, which is currently being used heavily in simulation, is floating frame reference formalism. It makes use of two well-known techniques. One is a finite element model, another one is a multi-body system dynamics. And the finite element is very good to describe small deformations with respect to reference coordinate system that is not moving anywhere at all. This is where the finite element modeling is very, very good. Multi-body system dynamics is very good to model this kind of reference motion, rigid body motion. When you combine these two methods together, then you're describing the deformation using finite element model. You're describing the large reference motion, rigid body motion, if you want to simplify that, with help of multi-body system dynamics. So that's how it works. Big problem is that if you look at this method in theory, like if you really look at that, it's changing the kinematics, because kinematics is now consisting of u bar 0, which is the one we looked earlier, that is defining where the particle is located, but there's a new component, and the new component is describing how the particle is moving with respect to the time. This one will be based on finite element model. This one and this one will be based on multi-body system dynamics. So this one is a multi-body system dynamics, multi-body system. Okay, and this is a finite element. So that's the combination. All right, so here it is explained. So you are describing this deformation with help of your finite element model. and you're describing your reference motion with help of your multi-body system dynamics. So you got the concept. Big problem is this. Typical finite element model consists of 100,000, sometimes million degrees of freedom. So the number of unknowns, this nodal displacement, is typically huge, is very, very big. Tens of thousands, thousands easily. Particularly what I learned recently is that solid elements are very much in fashion. And when you use the solid elements, your degrees of freedom becomes to be millions. It's going to be a lot regardless of how simple is the structure. And that's not great because here the number of unknowns for one body is, for planar case, is 6 or 7. And here it is 1 million. 6, or even in the worst case 7 versus the 1 million, they don't get along well. This is too big, way too big. So we need to do something for it. And something that is typically made for it is called modal reduction. And as the title implies, we're reducing the model size. And of course, always in a computation, you cannot get it all. Like in a life. Life and computational dynamics, you cannot get it all. In life, you can be, I don't know how it goes in life, but in computational dynamics, it goes like this. So if you get the high accuracy, it's going to be computationally very heavy. If you get the low accuracy, it's going to be computationally very light. So of course, you want to look for a compromise that the accuracy is acceptable and computational efficiency is acceptable. And the method that is used to get this okay compromise is a modal reduction technique. In a modal reduction technique, you are no longer looking about this nodal degrees of freedom, but you're looking the way the entire structure can deform. This is something that if you conduct an eigenvalue analysis to your finite element model, eigenvalue analysis tells you what are the natural frequencies and corresponding deformation modes. Then you can get these deformation modes. And these deformation modes can be considered as a way the structure can deform. Each of them can be considered separately, and this is how you can reduce the model size. How much you understood about that? That was clear, pretty clear, right? Okay, I'm not expecting you to understand anything at all, but here is a word of warning, because Jussi Sopanen is telling quite a bit more about this, how you're going to reduce the size of the model, how you're going to move from one space to another. Because when you're doing this modal reduction, you're going to move from one space, which is a nodal space, to something that is called modal space. I don't know if you can recognize it because of my accent. Nodal to modal. You hear the difference. Okay. I need to check later from the YouTube if it can understand that. Because I don't know if you noticed, but really it's helpful if you look at my videos and you put the closed captioning on. I don't know if you do that. Highly recommend it. So if there is a need to look at my videos, which I don't have that need really, but you might have this need. So highly recommend it to put the closed captioning on, because it is amazingly good how well it works. It can understand pretty much everything that I'm saying, almost everything that I'm saying. It really helps. But here's the beauty. You can put the closed captioning on in any language you want, including exotic languages like Finnish language. Okay? All right. This is it. I don't want to say anything more. Okay, because I want to leave it in this level. So it's this method that is heavily used is combining finite element models and multi-body system dynamics. What we do for the finite element model, we reducing the number of unknowns to be from 1 million typically to 10. How? We are using modal reduction techniques. Yes, we are losing certain amount of accuracy, that is correct, but still acceptable. How the trick is being made, you can learn this from correct simulation lab course. Okay, is it enough marketing? I guess it is enough marketing. I think I mentioned this course already, this class, number of times. Okay, now, next week. visiting lecture. I mean, there's going to be visiting, and then we're going to continue with that. Yes, sir.
Is there like a lecture notes the same way as for the first part?
Yes, there is. It's in my private folder. So I need to. It is actually in a Moodle, but I need to release it. It is available for hydraulics. Same kind of stories that. Yeah, it's kind of funny because I said that pressure relief valve. Go ahead and read it from the lecture notes, which is not visible at the moment. I'm gonna put it visible. Problem is this: my memory, like I said earlier, is very, very strong, but it's so short that as I'm back in my office, this is already gone from my head. So I don't remember to put it whistle. I mean, to make it visible for you. So if that's the case, send me an email. Response guaranteed within 24 hours. How you like about that service? Okay, this is it. So let's close the recording. We see on Monday 2 more times. The first one is a recap, and then comes the career counseling, which is no longer related to subject matter of this course. And then there's going to be coffee service also available 2 weeks from now. How that sounds? Okay. All right, guys. See you next week.
Thank you. Ja.